Welcome to the Deep Dive. Today, we're talking about something that feels like a genuine step change in AI. We're moving past large language models as we, sort of knew them.
Yeah.
We're strapping in for a deep look at their evolution from, say, a simple text-in, text-out tool into what we're now calling the truly autonomous AI agent.
And that's really the crucial distinction, isn't it? We're so far beyond the chatbot now. We're in the realm of systems that have genuine agency.
Agency, yeah.
So our focus today is all about the architecture. We're looking at the blueprints, what's actually needed to take these powerful independent systems from these, exciting but often brittle research concepts.
Right, the things you see on Twitter that break half the time.
Exactly. And move them into reliable, stateful, and this is the most important part, safe production environments.
Okay, let's unpack that. Our mission here is to really analyze the cutting-edge components that get you that reliability. You mentioned the core operation is different. It's defined by a kind of continuous loop, this iterative model. What does that cycle actually look like? Why is it so foundational?
It is, it's the defining characteristic that separates an agent from just a standard API call.
Yeah.
The whole thing runs on an iterative cycle of perception, reasoning, planning, and action.
Okay.
And this loop just runs continuously. It's what ensures the agent can maintain state and, dynamically adapt its approach based on feedback from the world or the results of its last action.
So perception isn't just seeing the prompt anymore. It's more like evaluating the current state of the whole project, looking at previous tool outputs, the overall context of the goal. It's like the agent looks around, figures out what's changed.
That's it, exactly. And then comes the reasoning and planning phase. This is where the LLM engine takes that perceived state and figures out the best next step. And that step could be really complex, involving multiple hypothetical moves ahead, which we'll definitely get into later when we talk about advanced planning.
And then action, the execution.
And finally, action. That's the execution, calling a function, maybe running some code, updating a database. The outcome of that action feeds directly back into the next perception step. That completes the feedback loop, the self-correction and adaptation. That's what makes them autonomous.
And then that leads us to what you've called the three defining features, right? The things that really characterize a true agentic system.
The first is autonomy. These systems can initiate actions without needing constant human input, without needing a prompt at every single decision point. It could be monitoring a project and deciding on its own, okay, I need to alert the team now.
So it has initiative.
It has initiative. Second is goal orientation. They aren't just, generating random text. They're engineered to work towards specific, defined outcomes. That could be summarizing a sales report, generating a new API endpoint, or diagnosing a bug in code.
And the third feature, tool integration. I feel like this is what gives them their real power, their connection to the real world.
Absolutely. Tool integration is the capability to call external functions, to query databases, to run code. Without this, they're just philosophers. With it, they're engineers.
I like that.
This capability is what transforms the agent from a language generator into a system that can take real, sometimes irreversible actions in the world.
That sets the stage perfectly. So we need to start with how these agents get their brains, all that knowledge they need, and then their hands, the tools they use to actually do things. Let's jump into section 1, the foundation of agentic intelligence.
Right. So when an agent gets a goal, its ability to succeed is, it's directly proportional to the quality and accessibility of its knowledge base. And we're not talking about static manuals here. We're talking about AI knowledge bases, or AKBs.
So if a traditional knowledge base is basically a digital filing cabinet, you have to manually curate it, organize everything, and you're just doing keyword searches, what gives the AKB its superpowers?
The difference is really the intelligence that's baked into the whole process, from ingestion to retrieval. An AKB is a centralized hub, and it uses pretty sophisticated AI and machine learning, especially natural language processing, or NLP, to process, understand, and then surface relevant information right when it's needed.
So it's not just storing documents.
No, it actually understands the semantic relationships within them. It automates a lot of the content management, which ensures accuracy in a way that, traditional systems just can't. And that's crucial for maintaining context and, importantly, reducing hallucinations.
And the sources feeding this system are super diverse, right? We can break them down into 3 categories, starting with the easiest one. Structured knowledge.
Right, so structured knowledge is all the information that's already systematic. So think articles, FAQs, organized manuals, procedural guides. This stuff is usually in a strict hierarchy or maybe a relational database, which makes it very easy to search in a traditional way. For an agent, this is the low-hanging fruit.
But the real challenge, and honestly where a lot of the most valuable data is in what you call the Wild West of unstructured knowledge.
That's where the NLP really has to flex its muscles.
Yeah.
Unstructured content, it has no predefined format. It's chaos. It's customer emails, raw chat transcripts, social media posts, multimedia files, even photos of whiteboards from a design meeting.
Right.
To get any value from that, the AKB uses these complex algorithms to find things like named entities, sentiment, intent, relationships. It turns all that noise into actionable insights that the agent can then use. Without that, an agent is really only seeing half the picture.
And the third type, automated knowledge, is really fascinating because it sounds like the AI is actively improving its own knowledge base.
And this is the hallmark of a really advanced self-optimizing AKB. Automated knowledge is content that's generated or curated automatically by the AI algorithms themselves. So think about a system analyzing thousands of support tickets, identifying a new common problem, and then it autonomously generates a suggested FAQ to address it.
Wow.
Or it could review how users are engaging with existing guides and suggest improvements, or even write summaries.
That seems like a massive win for efficiency. It
Yes.
turns the AKB from this static asset into a dynamic, living knowledge engine. It must cut down on the human labor needed to keep it current.
Precisely. It streamlines content creation, it ensures the knowledge base stays relevant, and it acts as this constant feedback loop for the whole organization to learn.
So the agent has its brain fed by the AKB. Now, how does it physically, reach out and interact with the world? This is where tool use comes in, and mostly through something called function calling.
Function calling is the primary translation mechanism. It's where the agent decides what to do next. The LLM, instead of just giving you back a conversational text response, it returns a structured instruction. Usually that's a specific JSON object.
And that JSON is basically a clean API call.
It's a very clear, precise API call. It specifies which external function to run and with what exact arguments.
Let's use a real example. If I tell a travel agent bot, find me the cheapest direct flight from London to New York for early October, the LLM isn't actually searching the web itself.
No, absolutely not. It uses its reasoning component to decide, okay, for this I need the flight search tool. It then generates the JSON, something like function flight search arguments,
Yeah.
with all the details, origin, destination, month, direct only. The orchestrator gets this, runs the actual flight search function, and then the flight data comes back to the agent in the next perception step.
Okay, so this capability gives agents 3 core powers in the real world: augmenting knowledge, extending their capabilities, and taking real actions.
Yes. Augmenting knowledge means it can query live, external databases, or proprietary APIs that weren't in its training data. Extending capabilities covers things like running complex, high-precision math, which LLMs are famously bad at, or doing sophisticated data analysis.
And the big one.
And crucially, taking real-world actions. Processing transactions, updating the state in an ERP system, or even controlling physical devices.
Function calling sounds pretty robust, but the moment you get into a big enterprise, you're not dealing with 3 tools. You're dealing with potentially hundreds of custom APIs, different LLM vendors, different security protocols. Doesn't scaling that become a huge nightmare to manage?
It absolutely does, and that's exactly the reason behind the Model Context Protocol, or MCP. MCP is this emerging standardization effort. It's aimed at defining and connecting external tools and data sources in a unified, consistent way, no matter which model or vendor you're using.
Okay, so why does standardization matter so much here, beyond just making things convenient?
It's really about trust and security. When you're dealing with hundreds of mission-critical systems, you need robust versioning, you need shared definitions, and critically, you need strong authentication and authorization that are enforced the same way everywhere. MCP just scales better than custom function calling because it's vendor agnostic. If you decide to switch from Model A to Model B, you don't have to rewrite and revalidate all your critical API definitions. The protocol handles that consistency.
That's a powerful argument for any enterprise looking at this. But let's get back to the core risk here. The output is still just a JSON blob generated by a language model, which is fundamentally unpredictable. It's stochastic. How do we make sure that instruction is valid before we execute something irreversible?
This is probably the most critical checkpoint in the entire agent architecture. Robust data validation. You just can't trust the LLM's output implicitly. The industry standard for solving this is to treat the LLM's function call output as a strict data contract.
A data contract. I like that framing.
Yeah, and that contract is enforced using frameworks like Pydantic, especially in the Python world. Pydantic uses standard Python type hints to define the exact schema, the data types, the required fields for every single tool.
So before that structured output moves an inch toward the execution layer.
It's validated. The logic makes sure that the JSON adheres precisely to the required schema.
So if the LLM hallucinates an extra field, or uses a string where it should be a number, or misses a mandatory argument like an account ID.
Pydantic throws an immediate validation error before execution. This prevents runtime failures. It protects your downstream APIs from getting junk or malicious inputs, and it transforms the unpredictable nature of the LLM's output into a deterministic, reliable structure that the orchestrator can trust. This level of defense it's non-negotiable for production systems.
Okay, now let's talk about something that raises the stakes even higher, the self-programming agent. This is moving beyond a predefined, trusted list of tools.
This is a significant leap toward, genuine unstructured autonomy. Most agents today rely on a fixed, curated toolkit. A self-programming agent, on the other hand, if it encounters a novel goal where it has no tool, say a really specific custom data manipulation task, it can dynamically generate raw, executable code on the fly to get that goal done.
Wait, hold on. If the agent can write its own code, it's not just an orchestrator anymore, it's a creator and a deployer. That sounds terrifying from a security perspective. Why would anyone choose that risk over just adding another trusted tool to the toolkit?
That's the critical trade-off. You choose this path when the problem space is just too vast or too dynamic for you to manually curate everything. Think about tasks like complex data science or solving these weird esoteric integration problems where the exact code you need is unique to the data set or the environment at that moment.
So adding a new tool every time is just too slow.
It's too slow and it's too costly. A self-programming agent is like a self-authoring executor and allows for immediate, flexible problem solving for, theoretically 100% of novel goals.
So the payoff is this incredible flexibility, but the risk is like running unvetted code from the internet directly on your core systems.
Precisely. The moment you execute dynamically generated code, you introduce enormous security risks. Privilege escalation, data exfiltration, denial of service attacks. All of that is on the table, even if the code was generated innocently, but just had a bug. This capability is only viable in production if it is paired with really robust isolation and sandboxing strategies.
What does robust sandboxing actually mean here?
It means the execution environment has to be completely isolated from the host machine and your production systems. We're talking dedicated virtual machines or containerized environments like Docker or even FireMaker micro VMs that operate with the absolute minimum required permissions, the principle of least privilege. And furthermore, these environments have to be short-lived. Spin up, execute the code, and then immediately destroy it. That prevents any kind of malicious persistence. This defense mechanism is what makes the self-programming agent viable at all.
The power is immense, but the architectural requirement for containment is equally strict. And speaking of architectural requirements, let's pivot to a challenge that undermines agent reliability even more fundamentally than tool risk: memory and statefulness.
Yeah, any serious discussion of advanced agents has to tackle the memory problem. For the last few years, the big solution for giving LLMs external knowledge has been Retrieval Augmented Generation, or RA. And it's been a revolution, but it hits a hard limit when we need true statefulness.
Okay, let's quickly just level set on RAG. RAG systems, they rely on vector databases to turn external documents like PDFs or knowledge articles into these high-dimensional vectors for semantic search. It's basically grounding the LLM's response, in fact.
That's right. And RAG is fantastic at retrieving static, factual information. It's brilliant for mitigating hallucinations. But that efficiency comes at a real cost when you're dealing with dynamic, evolving tasks. This is where we run into the memory wall.
Tell us more about this memory wall. Why do vector DBs fundamentally fail to provide the kind of true long-term memory that a complex agent needs?
They fail because they are optimized for one thing: retrieval of immutable chunks of text. They're not built for tracking statefulness or causality.
Right.
Statefulness requires you to track mutable variables, temporal dependencies, and synchronize dynamically changing state between collaborators. A vector DB can tell you what a document says, but it can't reliably track that a specific contract went from draft to pending approval last Tuesday at 3 p.m. and who made that change.
The knowledge it retrieves is static. It's like searching a library catalog versus tracking the minute-by-minute progress of a construction project.
Precisely. Imagine an agent that's tasked with managing a complex, multi-step process, say, a merger and acquisition. Over 3 weeks, that agent needs to track constantly changing valuation figures, the legal team's daily updates, the contact person whose role just changed.
And if all that information is just stored as text chunks in a vector DB, every time the agent asks what's the current state of the deal, it gets back 20 possibly conflicting or outdated snippets.
And the LLM has to waste tokens just trying to synthesize a current status, which might even be wrong. And that's where RG fails catastrophically. It can't reliably update the precise variables needed for an evolving task. It confuses versions, it misinterprets causality, it struggles to enforce dependencies. It just retrieves documents. It doesn't understand mutation. Agents need memory that's as dynamic and relational as our own working memory.
So we need a revolutionary shift away from this flat, document-centric retrieval. This is what you call the stateful revolution, defined by the memory graph.
The memory graph is a really rich data structure that's designed to mimic human cognitive models. So instead of storing memory as a flat list of text chunks, it uses graph databases to store information relationally. The memory has two core components, nodes and edges.
Nodes being the individual entities or concepts.
Correct. A node could be user John Smith, or Project Q3 launch, or preferred programming language, Rust. Edges are what define the rich relationships between those nodes. They capture causality and time. So an edge might be works on, prefers, updated, or supersedes. This structure lets the system traverse related memories intelligently. It connects the dots way faster than semantic search alone.
So it understands not just that John Smith and Rust exist, but that John Smith prefers Rust and that preference was established on a specific date.
Exactly. And this sounds like it requires a lot more intelligence during the ingestion phase than Argo. You can't just chunk and embed text.
Right.
And that's why the most advanced part is the process for intelligent updates and conflict resolution. When new information comes in, like a chat message, the architecture performs an extraction phase. An LLM analyzes the text and turns it into structured knowledge identifying nodes and generating relationship triplets. For example, John Smith changed preference to Python.
Then comes the intelligence layer. If John Smith previously preferred Rust, now you have a conflict.
Precisely. A simple system would just store both facts, leading to confusion. But here, a conflict detector flags that contradiction. Then, an LLM-powered update resolver intelligently modifies the graph. It doesn't just delete the old memory, it might create a new edge, like Rust, superseded by Python, and John Smith now prefers Python. This ensures the memory is always an accurate, current state of knowledge, tracking not just the facts, but the history of how they changed.
That seems to completely solve this supersedes that problem that cripples RG systems.
It does.
And that structural memory is essential for a single agent, but its value must just explode when you think about collaboration between multiple agents.
Oh, it makes multi-agent coordination seamless and reliable. In a complex enterprise setting, you might have specialized agents working at the same time. An architecture agent defining system design, an implementation agent writing the code, and a testing agent verifying it all.
So if the architecture agent changes the database endpoint,
that change has to be immediately and unambiguously reflected across all the other agents. With a single shared memory graph instance scoped to a specific project, any update made by one agent is instantly accessible to all the others. This establishes a single source of truth. It eliminates synchronization errors, prevents a ton of rework, and ensures consistency across the whole workflow. It's the difference between a synchronized team and 3 people working off different drafts of the same document. Okay, so the memory graph handles the long-term persistent state. But agents also need short-term memory, the context within a single LLM call. This is where cost and performance really hit hard, right? Because every token counts.
Yeah, managing short-term context efficiently is a constant battle for optimization. If the context window gets bloated with irrelevant chat history or these long descriptions of tools that aren't even needed for the current step, the agent's latency goes up and the cost per decision just skyrockets. Token costs are the primary constraint on OpEx. So what are the key practical strategies for managing this short-term context? You have to balance keeping crucial context with aggressive cost control.
The most fundamental and impactful strategy is just optimizing for output efficiency. Explicit brevity instructions. You build directives right into the system prompt that force the LLM to generate fewer tokens, to be concise. Cutting output tokens by 50% often translates directly to a 50% reduction in latency and cost.
What about the message history itself, though? You don't want to lose the thread of the conversation.
For managing chat history, the primary technique is trimming messages. This involves some complex logic to prune the context intelligently. A common way to do it is to keep the very first message, to establish the goal, keep the most recent few messages for continuity, and then just drop the verbose back and forth in the middle.
Right. That maintains the bookends of the task and the immediate action sequence. And the third strategy is maybe more resource intensive, but also more accurate.
That's summarization middleware. You use this when the history is just too long to trim effectively without losing vital nuance. You use a secondary, often smaller and cheaper, LLM, just to condense the long message history into a concise summary. It keeps all the key context, user preferences, critical facts, tool results, but it drastically reduces the token count you send to the main, powerful reasoning model.
It's really fascinating how the architecture has to manage both this persistent structural memory and this ephemeral, cost-sensitive context at the same time to be viable. Okay, let's move from memory architecture to cognitive architecture. How these agents actually make better, more deliberate decisions.
Yeah, so if an agent is just reacting sequentially, observe, think, act, repeat, it often struggles with tasks that need deep strategic planning, especially ones where early decisions have these huge cascading consequences. Methods like chain of thought or react are powerful, but they are fundamentally sequential. They lack any kind of look-ahead capability.
And this shortcoming is what led to the move toward deliberate planning, which is really embodied by the tree of thoughts, or 2T framework.
TOT is a pretty significant cognitive leap. It generalizes chain of thought by letting the LLM move past just generating a single path. Instead, it explores and maintains multiple coherent reasoning paths or thoughts at the same time. The agent doesn't just commit to the first idea it has.
It sort of plays out the possibilities.
It strategically evaluates choices, it can look ahead, and crucially, it can backtrack when one path turns out to be a dead end.
That mirrors how an expert human solves a really hard problem, like a chess puzzle or a complex crossword. You explore several possibilities in parallel, you rule out the failures, and then you commit to the most viable path with a high degree of confidence.
Exactly. And the performance jump is dramatic. There was research involving challenging problems like the game of 24. It's a numeric puzzle that requires some pretty non-trivial reasoning, and it showed that a simple, sequential chain of thought prompt with GPT-4 solved it only about 4% of the time.
Only 4%. Wow.
When they implemented the Tree of Thoughts framework, the success rate surged to 74%. That level of improvement just proves the value of this kind of deliberate, multipath planning.
A leap from 4% to 74% is astounding. But managing a tree of all possible thoughts must get computationally heavy very, very quickly. How do researchers make the search through that huge space efficient?
That's where established search algorithms come in. To avoid just generating this massive, chaotic tree, you integrate sophisticated search mechanisms. The most noted example is incorporating Monte Carlo tree search, or MCTS, which gives you MCT2. MCTS is crucial because it helps balance the exploration of new reasoning paths with the exploitation of paths that already look promising. It guides the agent's attention.
So TT gives you better quality reasoning, but because it involves multiple sequential LLM calls, one to generate paths, one to evaluate them, one to select the best, it must introduce a lot of cumulative latency. It makes the system smarter, but slower.
That's the unavoidable trade-off with deep deliberation, right? The sequential nature of most of these models, including 22T, creates a clear computational bottleneck. If step A has to finish before step B, and step B before step C, you're waiting for 3 slow LLM round trips and 3 tool executions.
And that challenge drives us to the next level of architectural efficiency. Graph-based agent planning, or GAP. How does GAP get around that latency and sequential bottleneck?
GAP introduces what's called dependency-aware reasoning. It fundamentally changes how the task is broken down. Instead of a linear chain or a search tree, the LLM agent is explicitly trained to decompose the high-level goal into an explicit dependency graph of subtasks.
Give us a real-world analogy for that. How does that decomposition actually make things more efficient?
Think of it like a factory production line, or even just a complex recipe. In a sequential model, you might be forced to slice the vegetables, then boil the water, then sear the meat. But a dependency graph lets you look at the whole recipe and see, hey, searing the meat and boiling the water don't depend on each other at all.
So the agent can identify that subtask B and subtask C are independent, even if they both depend on subtask A being done first. So it can execute B and C at the same time.
Precisely. It allows the agent to autonomously identify subtasks that can be run concurrently in parallel, and those that absolutely have to be sequential. This optimization is critical for cutting down that cumulative latency. It's the most aggressive approach to reducing wall clock execution time.
Do we have data on the efficiency gains from GAP over the sequential baselines?
We do, and the results are significant. GAP models achieve pretty substantial efficiency gains. They've been shown to reduce the number of execution turns, so the number of expensive, slow LLM round trips, by up to 33.4%. And because the planning is more structured, they also decrease the required output response length by nearly 25%. That kind of optimization makes these complex multi-hop reasoning tasks far more practical and economically viable for production.
Okay, so even with state-of-the-art memory and parallel planning, agents are still imperfect. Mistakes are going to happen. This necessitates robust self-correction mechanisms.
Robustness depends entirely on these internal feedback loops. The agent has to have the capacity to reflect critically on its own generated reasoning, often on its own chain of thought output, to identify and refine incorrect answers and prevent errors from propagating.
So the agent is basically its own internal QA team.
Effectively, yes. And research confirms that all forms of self-reflection improve performance, but the quality of the reflection is paramount. Simple try-again prompts just don't cut it. The agent needs detailed, structured feedback, much like a human receiving an expert critique.
And what specific types of feedback prove to be the most effective?
The measurable results show that reflection with detailed guidance significantly outperforms generic reflection. Specifically, reflection that includes detailed instructions on how to proceed, a full explanation of why the last attempt failed, or even a step-by-step solution to a previously failed attempt. Those yielded the largest improvements in accuracy. The deeper the critique, the better the guidance.
That's a key takeaway for anyone designing these prompts. Don't just ask them to check their work. Ask them to explain why they failed and how to fix it. Can you give us a real-world high-stakes example of this in action?
A great example is the Flow FSM framework, which is focused on cybersecurity analysis. Flow FSM uses LLM agents with iterative prompt chaining and reasoning to systematically extract highly accurate finite state machines, or FSMs, from raw protocol specifications, things like FTP or RTSP documentation.
And FSMs are basically the blueprints of how a protocol works, which makes them critical for finding vulnerabilities.
Exactly. The specifications are often verbose and unstructured. The agents process them, using internal reflection to construct these structured rulebooks, identifying all possible states like connected or authenticating, and all the valid transitions. This iterative refinement is critical because it forces consistency checks and minimizes hallucinated transitions. By applying this structured self-correction, Flow FSM achieves high precision, over 80% accuracy, and minimizes the critical error of hallucinating non-existent protocol behaviors, which could otherwise lead to massive security blind spots.
It's amazing to see this progression from sequential thinking to parallel planning with stateful memory and self-correction. It's like it's mimicking the increasing sophistication of human expertise. Okay, let's pivot to the practical reality of deployment. How do we actually operationalize these complex systems?
Right, because moving agents into the enterprise means the focus shifts entirely from novelty to reliability, auditability, and scale. And this requires selecting the right orchestration framework, which really determines the entire architectural philosophy.
The source material divides these frameworks into horizontal and vertical approaches. This seems like a crucial early decision. What defines that separation?
The fundamental difference is scope versus flexibility. Horizontal frameworks, like the foundational LangChain, are general-purpose toolkits. They maximize flexibility for all kinds of diverse experiments and rapid prototyping. You can build anything, but they demand a lot of engineering effort. For compliance or robust long-term memory, you often need to write hundreds of lines of custom glue code.
So if I'm a startup exploring a new use case, I start horizontal. High flexibility, but a high engineering tax when I want to go to production.
Precisely. Conversely, vertical frameworks like specialized platforms such as Agent Flow are purpose-built for regulated sectors. Think finance, healthcare, insurance. They sacrifice some of that flexibility for predictability and speed in these high-stakes environments. They come with built-in domain knowledge, native compliance features like audit trails, confidence scoring, and they often promise deployment in weeks instead of quarters.
That makes a ton of sense. Vertical frameworks are basically opinionated architecture for specific industries where compliance is non-negotiable. Now, within the general purpose, horizontal space, we see three major distinct architectural styles dominating.
Yes, and these represent different philosophies for how agents should interact. The first is CrewAI. This framework adopts a highly structured, orchestrator-driven model. It's based on defined roles and responsibilities. They call them crews and flows. This is the highly managerial approach.
So like a well-structured org chart, every agent knows its exact job and who to report to.
Exactly, and that rigidity is its deliberate strength. It's ideal for deterministic production-grade pipelines where compliance and repeatable execution are paramount. Because the workflow is so structured and centrally managed, it excels at enterprise scale. It can reliably support massive, concurrent agent workflows, often over 100 simultaneous tasks. It's the choice for high-volume, reliable business process automation.
Then you have the more free-form emergent model AutoGen from Microsoft.
AutoGen is pretty much the opposite. It uses a decentralized conversational model. Agents communicate by exchanging messages, almost like peers or colleagues in a chat room. This structure naturally encourages emergent collaboration and dynamic problem solving. It's excellent for research, for prototyping, for exploratory tasks where you want the solution to emerge organically from the interaction.
What's the trade-off for all that flexibility?
Well, AutoGen is generally less optimized for those large-scale, high-throughput enterprise workloads. While its flexibility is unmatched, the conversational overhead and the non-deterministic nature mean it has limited effective concurrency for mission-critical tasks. It often peaks around, say, 10 to 20 effective conversations before performance starts to degrade.
And the third major player, LangGraph, seems to occupy a middle ground, offering structure but without the same rigidity of CrewAI.
Yeah, LangGraph, which is an extension of LangChain, is a highly flexible backbone that formalizes agent workflows as graph-based state machines. This is a powerful, low-level approach. Instead of a conversation or a rigid crew, the developer defines the specific states an agent can be in, like planning, tool execution failed, review, and all the transitions between them.
And why is that state machine approach superior for certain systems?
It gives developers really precise, granular control over complex decision logic. It lets you create highly specialized custom agents in hybrid reasoning systems where, for instance, a task might bounce between an LLM call, then a proprietary legacy tool, and then a human review checkpoint. Its underlying asynchronous, event-driven architecture is highly scalable, and it's uniquely suited for managing these complex dynamic communication paths. If you need a custom agent that incorporates all the complex memory and planning we just discussed, LangGraph provides the ultimate scaffolding.
But regardless of the framework, we face that economic elephant in the room: cost and latency. The iterative nature of agents, all the sequential steps of planning, tool calls, introspection, it introduces this cumulative latency, and that just escalates the operational expenditure. This is a massive constraint.
It's the single biggest bottleneck to production viability. Every time the agent has to wait for an LLM round trip, and then wait for an external tool to execute, and then wait for another LLM intersection step, the latency just adds up. The system becomes slow and prohibitively expensive. That's why optimizing for fewer round trips is so crucial.
We mentioned generating fewer tokens earlier, but what are the deep architectural strategies to mitigate this cumulative latency beyond just asking the model to be briefer?
The second key strategy is Intelligent Request Optimization, or IRO. This involves aggressively consolidating multiple sequential actions or queries into a single, highly structured request.
Right.
Instead of asking the agent to, 1, find the customer's ID, then 2, check their order history, then 3, summarize their last 3 returns. You consolidate those 3 steps into a single prompt.
And you ask the model to return the result in a nicely parsed format.
Exactly. You instruct the LLM to process all that and return all 3 pieces of data in a structured format, like a single JSON object. This avoids 2 slow round-trip latencies, which is the biggest time saver in the whole process. IRO transforms the architecture from a slow conversation into a single, efficient data processing step.
And finally, we circle back to an architectural innovation we just discussed.
The third and very high-impact strategy is parallelization, specifically using graph-based agent planning, or GAP. By identifying non-dependent subtasks and executing them concurrently, the system maximizes resource utilization and dramatically reduces the total wall clock time. These 3 principles, fewer tokens, intelligent optimization, and parallelization, are non-negotiable for achieving economic viability at scale.
Now for the highest stakes subject of all: safety. Since these autonomous agents are designed to execute real-time actions like modifying infrastructure or transferring fund system failures can lead directly to financial loss, safety hazards, or major compliance breaches. What are the operational failure modes we really need to prioritize?
The risk changes completely because the agent is an active actor in the world. Failures aren't just inaccurate text, they are unintended execution. And operational failures can happen at any stage. The planning stage, where it incorrectly decomposes a goal, the tool selection stage, where it misinterprets a tool's capabilities, or the execution stage, where a malformed output leads to failure. This means we need layers of protection, not just one.
We call this a defense-in-depth strategy, and the critical first line of defense is the system of prompt guardrails against client-level attacks.
Right, and we can categorize these into input guardrails and output guardrails. Input guardrails are designed to prevent malicious users from manipulating the agent's core instructions. The primary threats here are prompt injection or jailbreaking, where a user input tries to bypass the system's rules, or code injection, where the input tries to force the agent to execute unauthorized commands. The guardrail has to filter, sanitize, and ideally classify the user's intent before that input ever touches the core LLM prompt.
And on the flip side, output guardrails are there to protect the company and the user from the agent itself.
Exactly. Output guardrails ensure compliance and data integrity. Their primary function is preventing data leakage, the unintentional exposure of PII, proprietary business secrets or sensitive tool outputs. They also enforce tool misuse boundaries, making sure the agent sticks to the principle of least privilege, even if its reasoning suggested a risky action. For instance, an agent designed for customer support should never be able to access the production database deletion tool no matter what a user asks it to do.
And when a failure does occur, detecting it in real time is paramount, especially for those high-stakes, irreversible actions. How is the industry prioritizing intervention?
Failure detection and intervention have to be calibrated intensely based on the reversibility of the potential failure. This is the most consequential distinction for agent safety. Scheduling a meeting is easily reversible. Deleting a production database, initiating a major financial transfer, or executing a critical code modification. Those are high-stakes, irreversible actions.
The moment the agent's action becomes irreversible, the required detection controls have to become multi-layered.
They demand the strongest real-time controls. For these scenarios, the architecture must include mandated human-in-the-loop, or HIL, checkpoints. This means the agent has to pause before execution and require explicit human approval for those irreversible steps. And furthermore, you need specialized controls, like an operator's watch mode, which lets a human observe the agent's actions and reasoning in real time and take over, or just halt the task instantly if the failure detection system flags an anomaly.
And finally, for the most safety-critical systems, we're talking aerospace, autonomous vehicles, critical infrastructure. Researchers are developing methods to provide theoretical guarantees on agent decisions. This takes us way outside of typical prompt engineering and into rigorous mathematical proof.
This is the absolute frontier of safety engineering. It's moving beyond empirical testing towards certified robustness. For these kinds of safety-critical applications, techniques like randomized smoothing are being employed. This is a statistical robustness certification technique that provides theoretical probabilistic safety guarantees on agent decisions, even in the presence of adversarial or noisy inputs.
How does injecting Gaussian noise actually provide a certification?
So randomized smoothing works by introducing controlled randomized noise into the input and then observing the agent's response across many iterations. If the decision remains stable and consistent across this statistically significant sample, that is, the agent consistently selects the same safe actions. Researchers can mathematically certify a radius of stability around that decision. This means they can assert with a design probability, say 99.9%, that even if a subtle adversarial influence were introduced, the agent's decision regarding a critical movement like turning left or braking would not change. It's a way to fundamentally mitigate hallucinations and prevent the propagation of malicious influence, providing a measurable scientific guarantee of stability.
That is truly the definition of moving from an experimental curiosity to a rigorous, trustworthy production system. This requires immense architectural depth.
Yeah, today we've covered the entire spectrum of this cutting-edge agent architecture. We established the foundational components, that iterative cycle of perception, reasoning, and action that grants true autonomy.
We then detailed the knowledge engine, moving from basic function calling to the standardizing power of the model context protocol. And we addressed the immense risk and reward of the self-programming agent, emphasizing that non-negotiable need for deep sandboxing.
We analyzed that revolutionary step past RAG, arguing that vector databases hit a memory wall. And the solution is the memory graph, a rich, relational data structure that enables causality, conflict resolution, and provides that crucial single source of truth for reliable multi-agent collaboration.
And finally, we explored the cognitive leap from sequential thinking to deliberate parallelized planning using tree of thoughts and graph-based agent planning. We wrapped up by detailing the frameworks, CrewAI, AutoGen, and LangGraph that operationalize these systems while implementing the necessary defense-in-depth security guardrails, especially focusing on irreversible actions.
Which brings us back to our final provocative thought for you to consider. The most consequential distinction for agent safety is the irreversibility of its actions. Since autonomous agents are designed to execute real-world functions at massive speed and scale, they have to be built with emergency brakes, agent rail checkpoints, operators' watch modes, real-time failure detection systems. But how can developers and regulators ensure that this necessary emergency brake remains effective, accessible, and reliably triggered, even as the agent's speed, autonomy, and complexity increase? Is there a critical point where the sheer scale and speed of agentic execution fundamentally undermines the efficacy of human intervention, making full autonomy the only viable yet most dangerous path forward?
A vital question for the architects of the future. Thank you for joining us for this deep dive. We'll see you next time.